Hey everybody, today we're going to go over some energy concepts. Now this is going to take us through some of the vocabulary that we need to know to look at all the different energy things that are going to be part of this particular part of the course. So we need to identify what energy is and give it a definition. Something that my 4th grade teacher had once told me was that energy is stuff that makes stuff go. And I always liked that definition. So stuff that makes stuff go. However, it's not the most sciencey of those, and so a more accepted definition is energy is the ability to perform work and transfer heat. Okay, so we can sort of see what it is, and we all have a general idea of what energy sort of goes for and what it looks like. But we can break it up into a few different kinds. So there's kinetic energy, so that's energy involved with motion. So if you have some sort of ball that's moving along here, so that involves with something that is moving. There's potential energy, and there's a few different ways that we can think about that. So if you imagine like a ball on a cliff, that's got very high potential energy, but this is also energy of composition. So that means that the energy that might be associated with certain kinds of high energy bonds, like things in hydrogen peroxide, that is energy of composition. Let me zoom in just a touch there. Okay? And then thermal energy would be energy that's associated with the heat of something or the temperature of something. So thermal energy involves temperature. Okay, and this is one of the things that your author does to sort of split these things up. But there's one basic thing to remember, is that no matter what kind of change matter is undergoing, there's a law of conservation of energy. And what that states is that energy is conserved. It is neither created nor destroyed. It is a property that is conserved. Okay? It can change forms, so it can go between being kinetic and potential and thermal and whatnot, but in total, the amount of energy that we have is not changing. So that's an important concept for us to remember. All right, so what's changing energy? What does it matter? So what we usually are interested in is some kind of system. That's an area of the world or the universe that we're interested in, and the system is in contact with some stuff around it. We usually call that the surroundings. And the system and the surroundings, they have the ability to transfer energy between each other. Okay, so for example, if I have a hot cup of coffee right here, it is able to exchange energy with my hand when it's in contact with it or the immediate area around it. But it's not going to heat up the hallway outside, not in any way that's really easy to detect. Okay? There are basic units for energy that we should pay attention to, and the SI unit for energy is the joule, Joule, given just the abbreviation here, J, and it's one of these units that's derived, so it's made up of 1 kilogram meter squared per second squared. That comes to us directly from the equation for kinetic energy. So if we have mass in kilograms and velocity, which is meters per second squared, that's kilogram meter squared per second squared, exactly what we see over here. So these two, this derives from this. Other units you may see for energy, these are what we call non-SI units. And we don't really, in this chapter at least, or this part of the course, we tend not to do a lot of conversions between non-SI and SI units. But it is still very helpful for you to know about it because lots of different disciplines will look at energy in different ways. So it's a good thing for us to know that 1 calorie is equivalent to 4.184 joules. And it turns out the definition of 1 calorie is the amount of energy needed to heat 1 gram of water 1 degree Celsius. And that's actually in a specific temperature range too. I think it's around 14.6. So that's the definition of 1 calorie, and that is equivalent to 4.184 joules. Notice that the calorie here has a lowercase c. When it has a capital C, that's what we often refer to as a dietary calorie. because that's when we measure our caloric content input for our, our daily diets. That capital C is in the place of a K, or kilocalories. So what that is 1,000 calories. So when you see on a food label that something has 1 calorie, it's one of these calories, not one of these. So it's actually a kilocalorie, which is 1,000 small calories. And then if you're in the habit of looking at your electric bill, 1 kilowatt hour is what we're looking at. And that's the amount of energy consumed in 1 hour, and that's equivalent to 3.6 times 10 to the 6th joules. Now you can go through and do a bunch of conversions on there, and that's all fine and good. We're really not going to worry too much about that. But we can look and see what sort of these things are sort of equivalent to. So let's say I'm trying to run a 10-watt light for 1 hour. In terms of joules, the energy, what does that cost me? Well, 3.6 times 10 to the 4th joules. If I did it in calories, 8.6 times 10 to the 3rd, or 8.6 kilocalories, or 0.01 kilowatt hours. And so I'm not spending a huge amount of energy, or at least money, because that's what I pay for on my electric bill, kilowatt hours, on that 10-watt light bulb for 1 hour. However, if we're looking at the amount of energy for a human to run 1 mile, that's me running a mile, sweating, but very, very fast. So I'm running a mile. In terms of joules, it's 4.2 times 10 to the 5th. So I'm really only an order of magnitude higher than running a 10-watt light bulb for an hour. So I feel like the punishment for leaving a light on in my house is 1 mile for every hour that it's on. That's the equivalent of about 10,000 calories. 100,000 calories. So 100 kilocalories, or 0.12 kilowatt hours. And then this is the amount used in a day by the average U.S. citizen. Now these are numbers that come directly from TRO. And they're very interesting. We use a lot of power on any given day. And this doesn't necessarily take into consideration all the other power that we end up using in a day. So for example, I have my little cell phone here, and there are other servers in other parts of the world that end up running to make sure that I get the data that I need. So it's not only the power that's in my pocket, it's the power that are powering the servers, so that I can connect with that and the entire Wi-Fi network. So I'm willing to bet that this number is actually a good bit higher than it is. But this watt, W-A-T-T, it's the rate of consumption of energy, or production of energy. And so when we talk about kilowatt hours, that unit of hour has to be in there. So it's joules used per unit time. Could be seconds, and then multiplying it by time again, so kilowatt hour, time times time, we come back to a unit of just straight up power, or joules. But kilowatt hour is what's used by our energy companies to figure out how much energy we're using on a regular basis. All of this gives rise to thermodynamics. And thermodynamics was this area of chemistry that was kind of wholly invented around the time of the Industrial Revolution to figure out how we can make better and more efficient engines. So thermodynamics is the study of energy and its interconversions. And one of the things to really realize in thermodynamics is that there are a number of rules. And the first rule of thermodynamics, so the first law, is that the total energy of the universe is constant. So what does that mean? Well, it goes very nicely with the law we saw before, which is that energy is neither created nor destroyed. What it means for us is that all the energy that's out there will always be there. And if we're going to talk about the internal energy of any particular substance, molecule, something along those lines, it's the sum of the kinetic energies and the potential energies of all the particles in that particular system. So if it's a gas, it's for each individual gas particle. And if it's anything else, it's all the different particles that make it up. So all the kinetic energy and all the potential energy for every single particle that's there. And internal energy is what's called a state function. And a state function is a value that depends only on the state of the system and not how it got to be that way. And that's a weird thing to try and wrap your head around. And most textbooks give an example like this, so like an elevation, for example, or a change in altitude. So if I'm, down here and then there's this mountain, all right? So there's a certain elevation here and there's a certain elevation here, and the difference in elevation is a state function, meaning that how I got here and how I got here in material. So if I were to just, be a really strong hiker dude and just go straight up this mountain, and now I'm here at the top planting a flag because now it's mine, that would be that the change in elevation is a state function. So how I got between these two places is not important. However, if I'm a smarter hiker, I will probably take a path that goes zigzags up the mountain. Probably fell off right there. But I zigzag up the mountain. Now, the number of steps that I took to do that would be very different. Okay, fewer number of steps going straight up, larger number of steps zigzagging across the mountain. So steps in something like this is not a state function, but a state function, like the difference in this altitude, that only depends on where I started and where I ended. And it's the same thing with chemicals and reactions. I have reactants and I have products in a chemical reaction where carbon and oxygen are combining to make carbon dioxide. So these reactants, when they come together, they end up losing some energy to become carbon dioxide. How they got to have this particular energy here and this particular energy here doesn't matter. There is a change in energy in this system, and that happens as a result of a reaction. So the delta E for this, or the change in energy, is what's known as a state function. So whenever we're trying to find the delta E for any particular kind of chemical change, it's always going to be our final state minus our initial state. And we usually do it from a particular point of view. So for example, if we have our system, and our system is losing energy to its surroundings, so imagine like a hot cup of coffee losing its energy to the surroundings and becoming colder, this is losing energy. So the delta E value would be negative in this case. On the other hand, if I have a cup of ice water, okay, so I got like ice and stuff in here, and the surroundings is warmer than the system, so it's heating it up, the change in energy here would be positive. All right, so that's something we want to keep in mind. We usually look at the change in energy from the point of view of a system. So point of view of the system. Now, with respect to how this actually happens, it happens in one of two ways. One of them is with heat and the other is with work. And we're going to go into definitions on what heat and work actually are later on in this chapter. Heat usually gets the symbol Q. Work gets the symbol W. We will do some calculations with heat. We're not really going to do calculations with work. So the system and surroundings, they can exchange heat. And that's one way that their energy would change. And they can exchange work. And that's another way that their energy can change. And so there are some sign conventions that are important to pay attention to. So if heat has a positive value, that means that the system gained heat. So the surroundings would have transferred some heat from it to that. Conversely, if it's negative, that means that the system has lost heat. So the system has given heat, or it's hotter than its surroundings and it gave heat this way. If work is positive, that means the surroundings did work on the system, so the system gained energy by having work done on it. And if work is negative, that means work was done by the system on the surroundings. Now we'll get into sort of what that looks like a little later on, but these are the ways in which that we can actually achieve a delta E for a system. But it's always important for us to realize the first law. The first law is the bane of our existence if we're trying to do things like lose weight, because all the calories we eat are always with us. So the change in energy of the system and the change in energy of the surroundings, because of the first law, will always add up to zero. So the energy that is gained by the system is equal to the energy that is lost by the surroundings. And so if we just subtract this, that means that the amount of energy here is equal to this, and then there's now a negative sign here. meaning that the energy gained by this system is equal to the negative of the energy lost by this system. So we can look at this in a number of different ways. So the energy of the delta E for a reaction would end up being the change in energy of the products minus the reactants. And the change in energy for really any kind of process is going to end up being something that is final minus initial. All right, so that ends the first little bit of what we're going to do here. That's all the different energy concepts that are kind of important. We're going to use these concepts to solve some problems in our next video. So go and look at that.